Now that we've started looking at some of the quantitative aspects of phase diagrams, we need to introduce a concept that will become useful not just for this chapter but for future chapters, and that is the idea of chemical potential. Chemical potential is looking at how does Gibbs energy change as you change the amount of a substance in your mixture. So that's how you say that vocally, right? Change in G as you change the amount of substances. And here we're not actually talking about specific substance, but amount of a substance in a particular phase for this example. So amount of a phase. And so this is now we're looking at how does G change with the number of moles of something, right? And so this sort of partial derivative where we hold everything else constant, so constant temperature and pressure, this is what we call a chemical potential. Now, the reason it is called a chemical potential is this is analogous to like a potential energy or electrical potential, like a voltage, if you've thought about that in terms of like electronics or electrochemistry. Similar to that, a system is going to tend towards the lowest value of chemical potential. Right? It's going to seek to decrease G because negative delta G means a spontaneous process. And so the lowest value of chemical potential will tell us, or chemical potential can tell us which way a process is going to go towards. So for example, a way we might set this up is thinking about what's G for a, something where we have a liquid-solid coexistence. Well, we can say G for the system is going to be G for the liquid plus G for the solid. Okay? And now we can say, well, what if we change the amount of liquid or solid that we have, right? We have a transition from gas to liquid, solid to liquid or liquid to solid. And so we could write this as, well, the change in G is going to depend, if we fix temperature and pressure to be constant at a particular given temperature and pressure, let's be clear here, we'll have a change in G of gas will depend on if we change the amount of gas that we have, keeping temperature and pressure and the number of moles of solid. Oh, I switched phases here. These should be liquids. My notes I was using gas. Okay. Times dNL. And we'll also have a change in the solid will depend on if we change the number of moles of the solid, keeping temperature and pressure and number of moles of liquid constant. Okay, so, but one thing we can say about this is that if we, number of solid. Okay, one thing we can say is that if we change the number of moles of liquid, it's going to have to go into the solid phase, and so we'll have this natural relationship here where these are equal and opposite to each other. So that means that we can rewrite this as dg is equal to a difference in these partial derivatives, dgl dnl minus dgs dns. Need the constant temperature and pressure here, times, let's see, this would be dnl. Okay, and so one thing we do, it gets tiresome to write these partial derivatives over and over, so we give this the symbol mu. Why mu? I don't know. So this one we would call mu L, and this one we call mu S. So these are the chemical potentials. And we can rewrite this expression as mu L minus mu S times dNL. Okay, and what can we say about this at equilibrium? Well, at equilibrium, we know that dg is equal to 0. That's sort of from our definition of spontaneity. Spontaneous processes are only if we have a negative delta G. if delta G is equal to 0, that's like a reversible process. That's an equilibrium. And that means, well, our moles of liquid can't be 0. So that means that mu L and mu S have to be equal to each other, right? So this is at equilibrium. So this is another way of looking at an equilibrium system, is that it's where chemical potentials are equal to each other. Okay? And if the phases are not in equilibrium, well, that means that either mu L is positive, or so if we're not at equilibrium, either mu L is greater than mu S, or mu S is greater than mu L, right? We have those are only options here. So if mu L is greater than mu S, what's going to happen? Well, that will give us mu L greater than mu S. They'll give us a positive value, right? If we're looking at this equation up here, if we have mu L greater than mu S, this term here will be positive. That would mean that this term has to be negative for this to be spontaneous, and so that means dNL will be negative, which means that some liquid will turn into solid. Because if we have a decrease in the number of moles of liquid, that means there has to be an increase in the number of moles of solid. And for the opposite version here, we get the opposite, right? That this will be negative and this will have to be positive, and we would get the opposite. dNL would be positive, and which would mean some solid would turn into liquid. What's generally true here is that whatever has the lowest chemical potential, right, the system will go towards whatever has the lowest chemical potential. And that is not just true for this two-component system or two-phase system that we're thinking about here. This is true in general, and gives us a useful tool for determining which way systems are going to want to go, depending on their value of G. And so that's something that's the power of this chemical potential idea. And it does not apply just here. We can use this idea of changing number of moles to look at reactions. That's when we get to reaction equilibria. Or if we're thinking about two-component systems or anything else, right? We're thinking about what's happening with chemical potential as we make changes to the system, and then the system will react in such a way to decrease or to go towards whatever has the lowest value of chemical potential.